Hi everyone, my name is Mark Vinciguerra. I'm a Specialist Solutions Architect at AWS on the ML Frameworks team, and today I will showcase how to efficiently orchestrate multi-user AI/ML training and inference jobs on a SageMaker HyperPod cluster orchestrated by EKS. This is a three-part video series where each part will cover the following ideas: overview of key ML concepts on AWS, distributed training on HyperPod, and inference on HyperPod. This video is the training segment, and I'll show you how HyperPod's training operator makes distributed machine learning resilient. We'll be training a llama model using FSDP, fully sharded data parallel, across multiple GPU nodes with automatic fault tolerance. Let me start by putting my training team hat on, as I'm another person now on this team. So what is the HyperPod training operator? The HyperPod training operator is a Kubernetes operator that reduces recovery time from minutes to seconds by implementing process-level recovery instead of restarting entire jobs when failure occurs. It surgically restarts only the affected processes rather than the entire job across all nodes. It also has enhanced real-time fault detection, where the system provides deeper integration with HyperPod's health monitoring infrastructure, enabling real-time instantaneous fault detection and eliminating latency previously caused by CloudWatch log processing. Finally, it has advanced performance monitoring and control, where HyperPod training operator continuously monitors metrics like stalled training batches, non-numerical loss values, missed checkpoints, throughput degradation, and allows customers to specify precise remediation behaviors through simple YAML configuration without code changes. The operator is already installed on this cluster, but in a real setup, you'd install it through the SageMaker console or during cluster creation. Before we can run our training job, we typically would need to build a container image with our training code and dependencies. I've built this already for time purposes, but let's take a look at the image. Pretend we are building an image from scratch to use on AWS. To start, we can use an NVIDIA NVCR image. This base image is known as NVIDIA's Container Registry, a repository for highly optimized GPU-accelerated software essential for AI, high-performance computing, and other accelerated workloads. It provides pre-configured and tested containers that significantly simplify and speed up development and deployment for developers, researchers, and data scientists. It contains the full CUDA toolkit, including compilers like MVCC, debuggers, and headers. On top of the base image, we install NCCL, NVIDIA Collective Communications Library, a library for high-speed multi-GPU and multi-node communication primitives, and it is essential for efficiently distributing the work of training a single large model across multiple GPUs or machines. The NVCR base image already has this, but I wanted to install a different version, so I included this in our image. It also has the EFA installer, which Elastic Fabric adapter, and this installs the necessary EFA drivers, tools, and allows EFA and NCCL-based applications to use libfabric as a network provider, enabling high throughput, low latency inter-node communication. There's also the NVIDIA GDR copy, and this library allows for zero-copy GPU to GPU transfers, bypassing the standard CPU-intensive CUDA mem copy operations. This reduces overhead and speeds up training, especially for small data transfers. And then we also have UCX. Although not needed, as NCCL has its own built-in communication methods, you can use the UCX plugin to enhance NCCL performance for inter-node communication by replacing its default transport with UCX's optimized RDMA-based routines. On top, we add our ML stack, which is the libraries for and requirements for our specific job. This includes the Torch library with FSDP for distributed training, the transformers for model handling, the datasets library if you want to stream a dataset from Hugging Face, and HyperPod's Elastic Agent for the HyperPod training operator. Finally, we are copying our training code and utilities into the container image. We're using fully sharded data parallel to train a 1 billion parameter llama model. FSDP shards model layers by distributing the parameters, gradients, and optimizer states of each layer across multiple GPUs, allowing us to train larger models than what would fit on a single GPU. Now that we have context what's in our container image, at this point we would build and push our image to our private Elastic Container Registry, or ECR, which would host the image. But we have already done this for the time purposes of this demo, so I'll skip over this. So currently, our cluster looks like this. We have our 10 ml.g5.8x large instances shared between the training and inference teams with no jobs running. So let's run our training job. So now we are in our IDE. I'll be using Kiro, but feel free to use whatever IDE you'd like to use. And we can start with just looking at our cluster again. So I'm running KGN, which is just an alias for kubectl get nodes. And we can see all of our nodes in our instances. We have our 10 G5.8x larges with the two M5.12x large instances. So I'm connected to my cluster, I've accessed them, and at this point, we can run our job. So we can look at our YAML. And by the way, all these jobs are publicly available. You can check them out on the links that we'll post under this YouTube video. So this YAML, it looks like a standard PyTorch job YAML, but it is of type or of kind HyperPod PyTorch job. And these are the type of jobs that work with the HyperPod training operator. So we give it that kind, we give it our name. We're training a Llama 3.2 1 billion parameter model with FSDP. And here is where we specify our task governance teams in this section. So we're giving it the namespace that our training team is dedicated to, and also the queue name and priority class. So you can see HyperPod NS training team. Here we're giving it the number of processes per node, which is the number of GPUs per node. In our case, it's 1 GPU per G5.8x large. And this part, the run policy, is specific to the training operator. This is where we tell it, the training operator, our rules and configurations to say when to restart at the process level, how many times to restart at the process level before restarting at the full job level, and when to do this. So if there's a missed checkpoint, it'll look through the logs and see if there was a missed checkpoint, and then restart at the process level. If there's a stall in starting the job, restart at the process level. So these are all of our configurations here. In our replica specs, this is where we're saying how many replicas we want, how many workers. We have our service account specified, where we have the MLflow service account. I'll show you that in a second. We also have our volumes mounted, and this includes our FSX for Lustre file system with our PVC. And if we go down, here's where we can see our registry image tag. This is our container image that's in our ECR right now. So when I deploy the job, it will pull the image and then run the job. Here we're requesting 1 GPU per worker pod and 1 EFA per worker pod, as the G5.8x large has 1 EFA available to give to the pods. Here we have our environment variables, some specific to nickel, some specific to EFA, our Hugging Face token. And on the command is where we see 2 sections of it. Starting with HyperPod run, this is specific for the training operator, and this is where we're specifying where we want our log directory to be, and then also nproc per node and end nodes. So under this, we have our train.py, and these are the arguments specific to our training job. This is how big we want our model to be, and the type of FSDP parameters and configurations we want to give our job, where we're storing our data set, and where we want to read and write checkpoints to. And that's an overview of our YAML. So now at this point, we can run in the training folder. I have submitjob.sh, which is just a env subst kubectl apply, because basically we want to substitute our in our environment variables into the YAML. And we could see HyperPod PyTorch job is created. So now there's a few ways to check how our job's doing and if it's running properly. First, we could see if there are pods running in this namespace. By running kubectl get pods in this namespace. And we could see 8 pods running. So this job is requesting 8 pods, 1 GPU per pod. So it's using 8 of the instances in our 10 instance cluster. So this is a good sign that it's running. How do we see the logs? You can run kubectl logs. There's also a tool called kubetail that you can use. And kubetail is just, it puts all the logs from all the pods together so you can display it all in one place. So I can run kubetail llama in our namespace. And we could see it started training. So it's on batch 3 with a loss, speed, and learning rate. So this is good. We've checked that there's pods running. We're checking the pod logs. And another method we can go is we can go back to the console. And in our cluster, we can look at our tasks. And we can select HyperPod training operator. And we can see with our job name, this is also running. And it has requested 8 GPUs. Another way to check, make sure our GPUs are running properly, there's good utilization, we can go back to our dashboards. So in our dashboard, we have our cluster. Here we'll be looking at the cluster dashboard, and we can look at GPU performance metrics. So I could filter this to go back to the last 5 minutes instead of 6 hours, refresh every 5 seconds, and we could see here utilization went up, and so has GPU memory, power, and utilization too. So we can see that here. And finally, I mentioned MLflow before. So SageMaker has a managed MLflow, and it has a natural integration with HyperPod. So I have a script here under MLflow that will create the UI. I already created the MLflow tracking server within SageMaker. But here we can run MLflow, create UI, and this will output our MLflow URL. So we can copy this, paste it into a new tab, and we see our job running here. This one 2 minutes ago. We can click on this. If we go to model metrics, we can look at our dashboards that we set up. And basically with this, what this is displaying is our learning rate, throughput samples per second, and our training loss. We can see here the samples per second is pretty consistent, and training loss is decreasing, which is a good thing. So this is how we can look at model metrics itself. So now our job is running properly. This is very good. But the whole point of HyperPod is it's resilient if something does go wrong. So I'm going to make something go wrong. I'm going to inject an error into one of our GPUs and see how HyperPod reacts to this. The way we do this is we are going to run training and node error. What node error does, it labels one of our nodes as unschedulable pending reboot. There's also unscheduled pending replacement. That's another option that HyperPod can replace the node instead of just reboot it, depending on the error. But that's what it would do. If there's a GPU error, it'll label that node. That's how HyperPod knows which node that is down. So that's what we're going to be doing manually. So in one terminal, I'm going to be looking at our logs again. So you can see it's still running. I'm going to open another shell. Here. And run this command. So it selected the GPU, or the specific node that's running our job. We could see an error here. Make this a little bigger. And we see it errored out. And it will start resuming from the last save checkpoint, as it's doing now. It saves the checkpoint every 10 steps. So it should, when it picks back up, it'll be at least 10. I forgot which time it started. Yes, this takes a second. You can see it found our data sets, found our checkpoint. And look, it picked up from batch 50. So I guess that's where we stopped at last. That's where it got its last checkpoint. And it is resuming the training from there. Oh, my phone just buzzed. It's a HyperPod alert. I've set up Slack integration in Amazon Managed Grafana to say, alert me whenever there's a GPU error. So it sends me the alert. HyperPod's going to start going to fix it. Once it's fixed, it'll tell me it's remediated. So you can see here this integration. So now, if we look at our cluster from a high level again, we have our training team occupying 8 GPU nodes. We see here that the training team was only allocated 6, but since there were 4 idle GPUs from the inference team, it was allowed to take 2 of them. They're idle, they're not being used, so the training team is borrowing them for right now. Now, at this point, it's the end of this video. Let's move on to the inference side of things.